Good afternoon, everyone. My name is Ben Potter. I'm an application engineer here at Concepts in Production, certified SOLIDWORKS expert, and today we're going to be taking a look at SOLIDWORKS Simulation. Specifically, we're going to look at design, validation, and optimization. We're going to begin by asking the question, will it break? After we have our design, we need to put it under loads and see that it can handle those. Then we're going to look at optimizing our design. Once we know it can handle the loads we're going to put it under, we need to see if we can lightweight it or streamline its design. Next, we're going to take a look at heat effect. So how can we add more to our study, maybe get more realistic world application that it'll be under. Then we'll look at determining material lifespan. This is useful especially for safety measures or maybe even like an alternate application we have for our design. We want to see how it can survive. And then finally, we'll look at report generation and see how easy SOLIDWORKS allows us to create reports straight from the studies we've created, as well as gathering all the useful information that we need. So in Will It Break, we're going to take a look at our monitor mount that we've designed, and it'll be within an assembly. So I'll show how we can assembly and use the different parts within it to our benefit or exclude them if we don't need them. Show how to set up a static study, as well as going into kind of looking at the results and gleaming the information that we can from that. So in SOLIDWORKS, we have our assembly here. We have the monitor, the base, and then a plate representing the table that it may be on. Simulation is built right into SOLIDWORKS once the add-in is turned on, and we'll just go and create a new static study. Now with the assembly, we have three components, and we don't need the table, so we can exclude it, and the monitor we can turn into a remote mass. So we can use the monitor itself, designating the center of gravity as where the heat is coming from, and that allows us to use it exactly as it would be in the real world. Adding in the weight of the monitor in the down direction. And then we need to add in our material for our base here. A 3D print this, we'll say. So we'll just do an ABS. And then next we need to add in our fixtures. So we'll add in onto our feet down here so that we know these replace the table. And also excluding the table allows us to not have to worry about meshing it and using up computer resources. Then we'll add in gravity. And then last we need to create a mesh. Now there's a lot of options in here we can do, but we'll just create a simple curvature mesh and make it pretty fine. And you'll see SOLIDWORKS is intelligent enough to know that these larger areas don't need a very fine mesh, whereas where it gets nice and tight, it will automatically create a smaller mesh for us. Now we have the entire study set up using the assembly components. We can easily go ahead and run this study. It'll take just a second. And now we have our results. We have a stress result, displacement, and a strain. And within that, we can go in and dig deeper. We can change our units if we need to. We can also do a true scale if we don't want to have this overly deformed model. We can add in our max so we can clearly see where the max stress is. We can even change how it looks. So we can get a lot of information from this, and we can designate how our plots, our result plots, look pretty easily. So we see that we're deforming very little and the stress is well within the material limitations. So our part easily holds up our monitor. So what this really comes down to is just eliminating the trial and error of prototyping, not having to create physical prototypes, which can be incredibly costly. We can create our designs and then model them, or once we've modeled them, we can then simulate them and when we do finally get to the prototyping stage, very easily and effectively be confident that they're going to do exactly what we need them to do. So now that we've created our original design and we've loaded it can withstand the forces, we ask the question, how can we streamline it? How can we lightweight it? How can we make it optimized? And that is the big question. How do you do that easily? We could sit here and remove material and try different variations in a kind of a manual sense, but that can take quite a bit of time. So we're going to go back into SOLIDWORKS and look how we can copy our static study we just created, bringing all of the fixtures and load data over, and pull that into what is called a topology study, where we will add restraints and goals that the system will then iterate for us, and we will arrive at a nice streamlined part. So within SOLIDWORKS, I can just right click on the study that I've already created and go ahead and just copy it. Selecting a topology study, it brings in everything that we had, the remote mass, gravity, the fixtures, but now we have goals and constraints as well as manufacturing controls. And under goals, a best stiffness to weight ratio, minimize maximum displacement, minimize mass with displacement constraint. We're going to do best stiffness to weight ratio, and we want to reduce our mass by 80%. So we want to really lightweight this part but keep the strength. And under manufacturing controls, we need to add regions to preserve. We need the top so the monitor can sit on it, and we also want to keep the back here, maybe for wire management or aesthetic purposes. And then we can also do a replane, because this part is symmetric on the right plane, and that way it'll speed up our iterations and processing time. The topology study is ready to go. We have our goals and we have our controls in place. Now this does take a bit of time to run, so I've already run it over here. And the way that it works is it does exactly what I mentioned. It starts to just carve out material and iterating over and over and over again based upon our goals and constraints until it arrives at a mass plot with as much material as it can remove, up to 80%. So we see we now have this nice streamlined part. And this is very useful as I decided to 3D print this part, as we can, 3D printing, the less material the part has, the cheaper the 3D print is. But also we can save this plot out as a graphics body or a step file, a STL file. And we can take this straight to the printer if we wanted to. Or we can go back into the model and actually overlay that mass plot on our model part and see how it looks within the full assembly. From here we could even begin to edit our part and use the mass plot as sort of a kind of a rough guideline to start removing the material. So we can do quite a bit with this topology study. And then once we're happy with it and we've done all of our changes, we now have our nice streamlined part. So the answer to the question of how do we go from our original design to that streamlined design is topology study. And it allows us to decrease the material waste, whether specifically in our application, the 3D printing, where we can remove a lot of material and also maintain our strength. Great for our application, but also translates down into basic CNC machining or traditional machining, where we can lightweight our parts for the end user. The top part, if that was a solid piece of metal, that'd be quite heavy, whereas the streamlined part is up to 80% mass reduction. So topology study is a very powerful tool that allows us to get these same strength but lightweight designs. So next we're going to look at heat. So in our application, we think maybe that we're going to our monitors are going to be all-in-one monitors. So all of the processing power will be housed in the base. And as we all know, computers, especially laptops, can get quite warm. So we've got heat now being applied to the top of our 3D printed part, and we need to factor that into our studies. Well, with SOLIDWORKS Simulation, we can bring in thermal temperatures and readings from previous thermal studies. And we're going to take a look at that. I'm going to show you how I set up a simple heat distribution through a part, and then how we can pull that into a static study and look at it, applying that load to it, and see the changes that it affects. So here we have our thermal plot where I've added convection, so that maybe out in a plant or it's got a fan on it. So I've added convection to it, and to all the surfaces except the top and the bottom of the feet, so all free surfaces. And then I've also added 100-degree Fahrenheit temperature along the top face. And we can run that study, and we'll see how the heat, distributes through. Pretty much the entire top part gets pretty warm, and we can now move into a thermal stress analysis, which is a static analysis where we apply that thermal load. And it's really easy to do that. So this was created by just copying our static study from earlier, or creating a new static study with this configuration, the new configuration, and then applying the same exact loads I did in the beginning. However, we can go in properties and we can add in the temperature from our thermal study. Thermal plot, thermal plot. And as you notice here, we can also add in temperatures from a flow sim. We can also add fluid pressure. So you can add quite a bit of information from other studies into these static studies to gain, deeper understanding of how the real-world application is going to be affecting our part. So everything is set, and we see an external load added to the thermal, or a thermal load added to the external load section. And we can now take a look at how this heat affects our part. So we see our max is in the back, and if we look at displacement, we actually see that with, the heat being kind of stored in the back of due to keeping this region, that it actually now also suffers the most, whereas in the original part the displacement was significant towards the front. So we now have a nice look at how the heat and the streamlined design can handle the monitor load. And so I can take that thermal plot and add it into a static study and get closer to real-world application, so that we're even more confident that our design will hold up into the situations that we want to put it into. Next, we're going to take a look at determining material lifespan. And this is going to be achieved by doing fatigue analysis. So the scenario here is, we know that our monitor mount can hold up to the monitor, but maybe a colleague of ours or ourselves, we see this and we're like, this kind of looks like a step stool. And we want to see, maybe we can print these and save money, but someone's going to be walking on this thing, quite a bit, up and down, cyclical loading, and we need to know what the safety of this is and if it can even handle that type of loading. And so we move into a fatigue study. And the way we do this is by creating a static study. But in this case, we've added a 300-pound load on the top face. So, fully grown adult, probably got gear, equipment on them, standing on this thing. And we've actually removed the monitor from it. And so we can take a look. We see the stresses are highest here, and this gives us a good indication of where the part will more than likely start to fail first. but this isn't, this may not be quite enough, and we really want to know the lifespan of this for PM purposes or safety purposes. So we can create a fatigue study in which we add an event. And in our event, we select the static study that we want, and we're going to run this through 500,000 cycles of loading and stepping off, loading, stepping off, so fully reverse. And we use an SN curve based upon the elastic modulus. You can create your own if you have your own experimental data, or there's plenty of database repositories online that supply this information. So you can create your own. You can use the standards just derived from elastic modulus. Some material has it already in there, so we can use this information to create our own SN curves based on however we wish to gain that information. And so with all that, we can now run the study, and it will run through 500,000 cycles of this study, applying the SN curve information, and we arrive at our damage plot. So we can see that after 500,000 cycles, quite a bit has reached 100% failure, damage failure. But what's really good in this is the life result. So we can come here and we see that the first action to reach 100% damage happens at 5,145 cycles. That allows us to know when we should expect failure, and this is really useful for any applications, as I mentioned, especially with PMs or safety, to know what areas to inspect, as well as when we should expect to have to replace parts. And so improvement of accuracy of failure prediction allows us to really dig into our designs and know where failure points can occur, when they may occur, and better handle those situations in planning for future events. So last we have the report generation. So report generation, we're going to take a look at how we can go just from a study and allow SOLIDWORKS to generate our report for us. It'll gather all the pertinent kind of background information that it has on our studies and put it into a nice, easy document that we can use, or we can use it if we have our own, customer template. We could generate the report and then actually just allow, pull the information off, allow SOLIDWORKS to collect the information for us and then pull it off. So here, we can, what information we want to add, a header information if we need it, and then we'll just go ahead and publish it. And so you'll see in the background, it'll take images and screenshots while it gathers all the other information. And it does this really quickly. I'll have to wait just a bit. Really nice and easy thing to do, as it gets every result plot. So if we added new results, or if we created graphs, then our results, all of that information, it'll pick up and put into this Word document for us. And the Word document it creates is fully editable, so we can go in and add in just better descriptions, conclusions, whatever we need to add to it. So you can see the description, we could add in our own if we wanted to. Scroll through here and we'll see the original model, the model that we analyzed, screenshots, assumptions. As you see, we didn't use a mean stress correction, then the study, the units we were in, the SN curve that we used. So all this pertinent information stored nicely into this Word document for us to use. The result plots. So it's real nice to have to easily grab all this information and put it into this format. And it really, gives us the power to maintain our document control and consistency, whether it's to always know that SOLIDWORKS is getting us the information that we need, or if we use the reports that SOLIDWORKS generates ourselves, the consistency of the format and again the information. So recap kind of what we just went through in Will It Break. We saw how we can eliminate our trial and error prototyping by being able to load up our designs and seeing the results and knowing even before any physical prototype is created where our model and design stands. Optimizing our design, we can decrease our material waste using topology. Allows us to really lightweight our parts, get that nice streamlined design for the end user. In heat effect, we saw the closer to real-world application, being able to say, heat will be applied to my model here, so we can see how it distributes through the material, and then even taking the next step in applying loads and seeing how the heated design survives within the loads that we are applying. In determining material lifespan, we have improved accuracy of failure prediction, where we can know when and where our parts are going to fail, and we can plan accordingly. And with report generation, we're able to generate those nice reports, maintain our document control and consistency. And then we'll have one more thing to show, and that is a drop test. So this is the more advanced simulations that you can do within SOLIDWORKS. So this is a roof section of a Resamen machine, and it is a kind of a self-contained vehicle that goes into mines and reinforces the roof. And so obviously, being inside of a mine, there's always a chance that you're going to have rocks dislodge and fall, and you need to ensure that the user is safe. And so we can go into SOLIDWORKS and create a drop test. So here the drop test has already been set up because it does take some time, but you can see all of the parts have been taken care of and meshed. We have all of our contacts and connections, how they would be in the real world, the different fixtures, initial conditions, face, how it's being held and then dropped, all of our controls, whether we're using dampening or not. So, a really detailed study here that we can then go in and look and see how, when this impacts, how the stresses fluctuate throughout our part or our assembly. We can look at displacement, and we can see that we're getting close to an inch of displacement, just a little under. And we can even take a cross section and see where our stresses are throughout our cross beams, support beams. And then we can look at a max deformation plot, and we see that we have plastic deformation. We have the material has yielded where the impact occurred, and we definitely from this information we can make informed decisions whether we need to maybe make things thicker or add in some sort of dampening type of design or apparatus. And then we can go in and actually animate our results, so we can see how the different stresses and deformations occur in real time. And we've already done that because it takes a little bit to render everything out. But here is the displacement. So as we can see, it impacts. We can see how the entire roof kind of flexes and returns, except for that centerpiece, which we know from our max deformation graph was deformed in the plastic region. So next we can take a look at the section view, so we can see how little support channels, how they take the load, and how it distributes throughout. And then kind of the coolest picture is definitely the full stress throughout the entire assembly. So we can really see how and where the stress is being applied and distributed throughout the entire impact. So we know, these areas over here go up into the high stress. We may need to make them more robust, add in that dampening. So it really allows us to interrogate our designs. And this just shows the power that SOLIDWORKS has with being able to do something like this drop test. So at the end, we are able to get to our nice, streamlined design with the confidence that it will hold up to all the applications that we have designated for it. So thank you for attending the webinar today.